Welcome to this number theory primer. In this lecture, we will discuss a very important notion called the notion of congruences. Um, and let us recall one definition that we need in order to understand today's lecture. So, given a relation tilde on a set X, we call it an equivalence relation if it has three properties. That tilde is reflexive, which means that x tilde x for all x in X, and tilde is symmetric, which means that if x tilde y, then y tilde x for all xy in the set, and tilde is transitive, which means that if x tilde y and y tilde z, then x tilde z whenever we choose x, y, z in X. So this should be familiar to you. If not, you can, I'm sure I have made a video about this, or you can Google or something, but yeah, this is a very important concept in all of mathematics. You will see it everywhere. So once we have an equivalence relation tilde on a set X, the equivalence class of X is defined as, this is the notation, generally this is used, but one may use a different notation. And the definition is all the things in X which are related to X. So it's a very simple definition. And the set of all the equivalence classes partition the set X. So once you have an equivalence relation on a set, you also induce a partition of the set X. And in fact, there's a simple correspondence between the set of all the partitions of a given set and the set of all the equivalence relations on the given set. Anyway, so this is just a recall. Here are two problems for practice. And now let us get started. So fix a non-zero integer, n, and define a relation which we have denoted this way. It's not, we don't use tilde, we are using three horizontal lines and a subscript n. So this relation is on the set Z of all the integers, and the relation is defined as follows. We say A related to B if n divides A minus B. So if the difference of A and B is divisible by n, we declare A and B related under this relation. Okay, and here is just a notational thing. Instead of writing this, we may write that. And how do we read this? We read this as, this is read as A is congruent to B modulo n. So from the point of view of n, A and B are the same. A and B are equal as far as n is concerned. You can think of it that way, right? So that's a notation, and this was introduced by Gauss, so a great mathematician from antiquity, Carl Friedrich Gauss. I encourage you to read about him on Wikipedia or some other article. So he introduced this in his book Disquisitiones Mathematicae or something like that. I can't pronounce it very well. And he proved a lot of new results in that one book. Anyway, so here is a simple lemma, that this thing is an equivalence relation. So this is a relation on Z, and this is an equivalence relation. This is a very simple exercise, but let me at least sketch it. So why is it reflexive? It is reflexive simply because if A in Z, then n divides A minus A, because n divides 0, and therefore A is related to itself under this relation. Symmetric. So suppose A and B are in Z, such that n divides, such that A and B are related, and we want to show that B in the symbol A. This is what we want to show, but what that means is that n divides A minus B, which implies that n divides B minus A, which implies that B is related to A. Very simple. And transitive, also very simple. So fix A, B, C in Z such that A is related to B and B is related to C, then n divides A minus B and n divides B minus C. And now since n divides these two things, it also divides the sum of these two things. So n divides A minus B plus B minus C, which implies n divides A minus C, which is nothing but A is related to C. So it's reflexive, symmetric, and transitive, and by definition this means that this guy is an equivalence relation. So it's an equivalence relation, and notationally we just commented that this is how we notate. Typically we will not use this notation. Anyway, so what are the equivalence classes? We have an equivalence relation. Can we give a description of the equivalence classes? So fix a non-zero integer. Then the equivalence classes, then the equivalence class of a given integer is nothing but this guy. So you take any multiple of n and just add a to it, and all such numbers form the equivalence class of a, and we typically denote it by a bar. So of course this notation loses the integer n. Of course the equivalence class is sensitive to what n you picked. The equivalence relation is determined once you fix an n, but here for simplicity we do not qualify this notation with the n that is in the background. Okay, before we proceed, let's see what this means for a particular example. So suppose we take n equals 2. For n equals 2, what is the equivalence class of 1? So 1 bar is the equivalence class of 1, and this is all odd integers. You can just verify this. All odd integers. And 0 bar, the equivalence class of 0, is all even integers. So that you can see from this description or directly. So for n equals 2, it's just capturing the parity. The equivalence class is just capturing the parity of the integer. Anyway, and this is very easy to prove. This is also an exercise, but again, let me at least sketch it. So clearly, okay, or before I go there, let us write S as this set. Well, I've already written it as a bar, but let me write that as S. And if we pick something in S, let me call it little s. So if this is an S, then S minus A is divisible by n. This is clear because S looks like that, and if you subtract A from it, you get something that is divisible by n. So n divides S minus A, and that implies S is related to A, and therefore everything in S is related to A, and therefore S is contained in the equivalence class of A. Right? So I hope you followed this. We showed that everything in S is in the equivalence class of A, and now for the reverse containment, suppose pick something in the equivalence class. Let's maybe denote it by B. So then n divides A minus B, because A and B are related, which implies, or let me write that as B minus A, doesn't matter, it's the same thing. So that means B minus A is equal to nk for some k, and thus B is equal to nk plus A, which implies B is in S. So all of this shows that the equivalence class of A is contained in S. So now this and that together imply that S is equal to A. I mean, S is equal to the equivalence class of A. And that's it. That is what we wanted to prove. So we will use this notation. We will not use the bracket notation. We will use this notation from now on. All right. So here is the reason why this is very useful. There is an algebra that you can play with this notion. So fix a non-zero integer, and suppose we have 4 integers a, b, c, and d, such that a is congruent to b modulo n, meaning n divides the difference of a and b, and c is congruent to d modulo n. Then it behaves well under addition. So you can add a and c and you can add b and d, and the two summations are congruent to each other modulo n, and it also behaves well under products. So you can multiply the first two things and you can multiply the second two things, and you see that. Yeah, so this is the statement that it behaves well under sums and products, which is what makes it so powerful. And the proof is again a very simple exercise. So a congruent to b modulo n implies that a is equal to b plus nk for some k, and c is equal to d plus nl for some k and l in integers, right? So because a and b are related, they are in the same equivalence class, or you could say that b is in the equivalence class of a, and we just showed that everything in the equivalence class of a looks like this. So well, I've done it in the reverse way. I'm thinking of a in the equivalence class of b is the same thing, but still a is in the equivalence class of b, therefore a can be written in this way. C is in the equivalence class of d, therefore c can be written in this way. And now it's just to prove the addition thing. This shows that a plus c is equal to b plus d plus n times some integer k plus l, and this implies that a plus c is congruent to b plus d modulo n. And similarly for the product, so AC is equal to what? AC is equal to b plus nk times d plus nl is equal to bd plus something divisible by n. So skipping a step, what it would be bl plus, it's irrelevant what it is, but anyway I have to write it, kd I think plus n kl. I think this is what you'll get, but anyway it's just n times some stupid integer, we don't care, which implies AC is congruent to BD modulo n. That's it. That's the proof. So it's a very simple argument. And the corollary of this lemma is this, that again we have a non-zero integer, we have two integers a and b, such that a is congruent to b modulo n. Then for all positive integers, in fact for all non-negative integers, you could say that a to the k is congruent to b to the k modulo n. K is equal to 0 is also fine, because then this becomes 1 and that is also 1. But I've stated it only for positive integers. So how do you prove this? Basically what you have is, let's do it for k equals 2. So what you have is a congruent to b modulo n, and you also have a congruent to b modulo n. Modulo n. Right? If you have a congruent to b modulo n, then you have a congruent to b modulo n. Surprise. So now just we have these two things, and therefore if we product, we have a times a congruent to b times b. So a square is congruent to b square modulo n, and you can just keep bumping this up. So I leave all the details. All right. And now let us see examples where we use this thing. So first is 41 dividing 2 to the 20 minus 1. Now this looks a bit daunting, because 2 to the 20 is a big number. If you calculate it, you can calculate it, I think. You'll be able to write it down, and then you can divide it like you do in high school and show that the remainder is 1, and therefore you'll have shown this. But using modular arithmetic, this is much, much simpler. So what we have is the following. 2 to the power, let's see. So we have 2 to the power 5 is 32. What is 2 to the power 6? 2 to the power 6 is 64, and 64 is congruent to, so this is congruent to 23, I think. 23 modulo 41. Let me check. Yeah, this is correct. So 2 to the power 6 is 64, I hope. And 64 is congruent to 23 modulo 41. Because if you subtract 64, if you subtract 23 from 64, you get 41. All right, so 2 to the power 6 is congruent to 23 modulo 41. And thus 2 to the power 7 is congruent to 23 times 2 modulo 41. What did we do? We multiplied 2 on both sides. So here maybe I should have stated another corollary. Basically, here is what I'm using. If A is congruent to B modulo n, then MA is congruent to MB modulo n for all m. This is all that I'm using, and this is very simple because all you do is you have m congruent to m modulo n trivially, and now you multiply A with m, you get MA, you multiply B with m, you get MB, and therefore you have that. So we can multiply both sides by a fixed integer, and that's what I did. I multiplied here by 2, I get that. I multiply here by 2, I get that. So what is this? This is 46. So 2 to the 7 is congruent to 46, and 46 is congruent to 5 modulo 41. And now again, let's see, 2 to the power, let's just square both sides. So 2 to the power 7 square is congruent to 25 modulo 41. We squared both sides. As we saw, we can raise everything, we can raise both sides to the power k for any positive integer k. We raised both sides to the power 2. So this is nothing but 2 to the power 14, and 25 is 25. So now this gives us 2 to the power 15 is congruent to 50, which is congruent to 9 modulo 41. Again, all we did is multiply both sides by 2. This becomes that, and 25 times 2 is 50, which is congruent to 9 modulo 41, because the difference of 50 and 9 is 41. All right, and now finally we can, so let's do it directly. So now we multiply both sides by 2 to the power 5 modulo 41, and 2 to the power 5 is 32. So what is 9 times 32? It is 9 to the 18, 278. And what is the remainder of 278 when you divide it by 41? So 41 times 7 this is 288, sorry. So 41 times 7 is 287, and therefore this is 288 is congruent to 1 modulo 41, right? So here we had 2 to the 20, here we had this number is 2 to the, this number is 288, and if you just calculate, 288 is congruent to 1 modulo 41 because their difference is divisible by 41. And all this computation shows that 2 to the 20 is congruent to 1 modulo 41, and that is the same as this statement. So we did not need to compute very, very high powers of 2 in order to calculate this remainder. There are other ways to do this. There is a much shorter way to do this, but we will learn that later. All right, the second one is this. We have this horrible number, and we want to show that when we divide it by 12, we get a remainder of 9. And here we have absolutely no hope to compute this number and then divide. There at least we had some hope. But here there is absolutely no hope that you compute this number and then divide it by 12. It will be a lifetime. But here is the thing. Note that if n is greater than or equal to 4, then n factorial is congruent to 0 modulo 12, which means that n factorial is divisible by 12. Why is that? Because 4 factorial is 24, which is divisible by 12. And 5 factorial is divisible by 4 factorial. And therefore, it is also divisible by 12. So, same goes for 6 factorial, 7 factorial, and so on. So, every integer greater than 3 has this property. And therefore, this horrible sum, n from 1 to 100, n factorial is congruent to 1 factorial plus 2 factorial plus 3 factorial plus 0 plus 0 plus 0 plus 0, and therefore we don't need to write it, modulo 12, right? This one is congruent to that, this is congruent to that, this is congruent to that, and everything here is congruent to 0, so that just becomes a 0, and we are left with this guy. And what is this? This is 1 plus 2 plus 6 modulo 12, which is 9 modulo 12, and that's it. So whatever is this number, if you subtract 9 from it, you get something divisible by 12, and that is same as saying that 9 is the remainder when you divide it by 12, because 9 is between 0 and 11. So it has to be the remainder. So this is very powerful. Modular arithmetic is very powerful. Alright, so that's all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.